Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Master's Degree Programs. M.Sc. Applied Statistics, MSCAST Semester I. MST-11 Real Analysis, Calculus, and Geometry. Block-1 Real Analysis. Unit-1 Function of a Single Variable. 1.1 Introduction. In statistics, we use parameters for population characteristics such as mean, variance, etc. Constants and variables are also used in statistics. So, it becomes important to understand the distinction between fixed constant, parameter and variable, which is discussed in Sec. 1.2. Another important thing that we are going to use on many occasions in different courses is the interval. In Sec. 1.3 different types of intervals are discussed. To understand many concepts of probability and statistics such as probability mass function, probability density function, cumulative distribution function, likelihood function, etc., you should have a good understanding of function. Therefore, a brief overview of the function is given in Sec. 1.4. There are some special functions which have their applications in statistics, probability and machine learning, such as linear, polynomial, logarithm, exponential, modulus functions, logistic, sigmoid function, etc., which are discussed in Sec. 1.5. In the course MST-024. On machine learning, you will also use many other functions such as loss function, distance function, Manhattan distance, Euclidean distance, Chebyshev distance, etc. The distance function is discussed in Unit 3. What we have discussed in this unit is summarized in Sec. 1.6. Self-assessment questions, SOCs, have been given in some sections which are generally based on the content discussed in that section. But to give you a good practice of what we have discussed in this unit, some more questions based on the entire unit are given in Sec. 1.7 under the heading Terminal questions. One of the characteristics of IGNOU study material is that it is self-contained. To make it self-contained regarding solutions of all the SOCs and terminal questions, we have given solutions of all the SOCs and terminal questions of this unit in Sec. 1.8. To best utilize this section, it is recommended that after going through all the concepts discussed in the unit, first you should try solutions of all the SOCs and terminal questions yourself. In the case your answer does not match with the answer given in the solution of the same, you may give it another try. If still not matching, you may refer to the given solution and identify the concept where you need to improve. In the next unit, you will study types of functions, countable sets, continuity, and differentiability of a function. 1. 2. Constant and variable quantity. Suppose someone wants to know about you, then perhaps he or she should know your name, the background of the family you belong to, your educational qualifications, how good as a human being you are, other achievements, etc. Similarly, if you want to know/study the subject statistics, then it requires that first, you should have an understanding of some rules of mathematics. Understanding these rules of mathematics will make the journey of studying tools/techniques of the subject of statistics easy as well as interesting. Understanding which tools/techniques of the subject statistics will apply in a given situation is a long journey. Purpose of different courses of this master's degree program M.Sc. Applied Statistics is to start this journey smoothly and in a sequence. Understanding the mathematics rules required to study statistics is not hard if you start from the basics. In fact, when you start from basic, learning any subject becomes interesting and creates a hunger to learn more and more. Like your name, the subject that we are going to discuss here also has its name called mathematics. Unlike your one family, learning mathematics starts from knowing about its many families called families of numbers. You know about these families of numbers from your school mathematics. Let us recall these well-known families of numbers mentioned as follows. Family of natural numbers equals 1, 2, 3, 4. 1.1. Family of whole numbers W equals 0, 1, 2, 3, For 1.2, family of integers, equals 3, 2, 1, 0, 1, 2, 3. 1.3, family of irrational numbers, a number on the real line which cannot be expressed in PQ form where P and Q are integers and Q is not equal to 0 is called an irrational number. In books on mathematics generally, no notation is specified for the set of all irrational numbers like Q is used for the set of rational numbers. 1.5, family of real numbers, R equals Q union I where represents the set of all irrational numbers. 1.6, family of complex numbers, C equals plus, A plus IB, A, BER, where the symbol I is read as iota and denotes the square root of 1, I, E, I1, equals under root minus 1 with I square equals minus 1. 1.7 Note 1. In higher mathematics, family of natural, integer, rational, real and complex numbers are denoted by the symbols N, Z, Q, and C respectively. After getting the idea about these different families of numbers, the next thing that you should be familiar with is the meaning of constant and variable. Actually, you have used them so many times in school mathematics. Here, we are discussing them because we want to further classify them. In fact, they are a particular type of quantity, so the story begins by defining the quantity itself as follows. Quantity in mathematics and statistics. Quantity means those things on which 4 basic mathematical operations, addition, subtraction, multiplication and division can be applied. For example, I, 2, 5, 2, population mean, mu3, number of children per family, 4, all real numbers between 2 and 3 including 2 and 3, etc. all are examples of different types of quantity which you will come across during your study of different courses of M.Sc. Applied Statistics program. A quantity can be classified as a constant or a variable quantity. Constant quantity can be further classified as fixed constant and arbitrary constant/parameter. Variable quantity can be further classified as discrete and continuous. All these classifications are shown in Figure 1.1. Constant quantity, a quantity which remains same, unchanged, throughout a particular problem or distribution is known as a constant quantity. A constant quantity can be further classified as a fixed constant and arbitrary constant, also known as a parameter, which are defined as follows. Fixed constant, those types of constants which always remain the same, unchanged, independent of the place and time are known as fixed constants. For example, 2, 3 upon 2, under root 13, minus under root 17, pi etc. are fixed constants because the number 2 will remain the same whether you use it in the morning or evening or in India or in any other country. Similarly, the number which is equal to the quotient of the circumference of a circle, 2 pi r, and its diameter, 2r, is a fixed constant. Value of does not depend on the length of the radius of the circle. Also, remember 22/7 is not the exact value of it, is just an approximate value. Exact value of pi equals length of circumference of the circle upon length of diameter of the same circle. Arbitrary constant or parameter, those types of constants which remain the same in one problem but may vary from problem to problem or distribution to distribution are known as arbitrary constants or parameters and are generally denoted by A, B, C, L, M, N, 2, etc. For example, from school mathematics, you know that the equation y equals x plus c represents a straight line which makes an angle of 450. Slope is 1 equals coefficient of x if we compare it with y equals mx plus c, with a positive direction of the x-axis. For each real value of c, this equation gives a different straight line. Refer to Figure 1.2. Here, c behaves like an arbitrary constant because for a particular line, its value is a fixed constant but its value varies from line to line. Similarly, in normal distribution mean, mu, and variance, sigma 2 are parameters because they remain fixed constant in a particular normal distribution but vary from normal distribution to normal distribution. Refer to Figure 1.3. Variable. A quantity which may change its value even in a particular problem is known as a variable. For example, in the quadratic equation x square, x, 12 equals 0, x is a variable because it takes two values 4 and minus 3. A variable can be further classified as discrete and continuous, explained as follows. Discrete variable, if the nature of the quantity is such that its possible values can be written in a sequence, then such a quantity is known as discrete in nature or discrete variable. For example, the number of children in a family in a country may be 0, 1, 2, 3. Here, you know that the minimum possible number of children in a family is 0, and after 0 the next possible value for the quantity, the number of children in a family, is 1. There is no possibility between 0 and 1 for the quantity, the number of children in a family. Similarly, after 1 the next possible value for the quantity, the number of children in a family, is 2, and so on. Here, you can write the possible values in a sequence 0, 1, 2, 3. So the quantity, the number of children in a family, is a discrete quantity and so is an example of a discrete variable. Other examples of discrete variables are the number of accidents at a particular site on a road, the number of defective items in a packet of 100 items, the outcome of a die when it is thrown once, etc. Continuous variable, if the nature of the quantity is such that it can take any possible value between two certain limits, then such a quantity is known as continuous in nature or continuous variable. In other words, if a quantity is continuous in nature, then you cannot write all its possible values in a sequence. For example, you cannot write all real numbers from 2 to 3 in a sequence. In fact, you even cannot tell what is the next possible real number just after 2. If you say 2.1 is the next real number after 2, no, it is not the next real number after 2 because 2.01 is between 2 and 2.1. If you say 2.01 is the next real number after 2, no, it is not the next real number after 2 because 2.001 is between 2 and 2.01. Similarly, if you say 2.001 is the next real number after 2, no, it is not the next real number after 2 because 2.0001 is between 2 and 2.001 and so on. The more advanced mathematical distinction between continuous and discrete quantities can be understood after getting an idea of countable and uncountable sets discussed in Sec. 2.3 of Unit 2 of this course. Other examples of continuous variables are temperature, height, weight, age, etc. 1.3 Interval and its types. Types of intervals. Intervals are classified on the basis of two criteria. A. Whether it contains its endpoints or does not contain its endpoints. B. Whether its length is finite or infinite. Based on these criteria, different types of intervals are defined as follows. A. Different types of intervals based on the criteria of whether it contains its endpoints or does not contain its endpoints. On the basis of endpoints criterion, an interval may be classified as an open or a closed or a one-side open other side closed interval defined as follows. Open interval, an interval I with endpoints A and B, a less than B, is called an open interval if it contains all real numbers between A and B but does not contain endpoints A and B. An open interval with endpoints A and B is denoted by A, B, and mathematically is defined as follows. A, B, X. AXB equals 1.10. For example, open interval 2, 5 contains each real number lying between 2 and 5 but does not contain 2 and 5. To represent an open interval on real line, we make open dots at both endpoints. Figure 1.4 A indicates it on the real line. I, E, X, 2, 5, 2 by 5 closed interval, an interval I with endpoints A and B. A less than B, is called closed interval if it contains all real numbers between A and B and also contains endpoints A and B. A closed interval with endpoints A and B is denoted by A, B, and mathematically is defined as follows. A, B, X, AXB, equals 1.11. For example, closed interval 2, 5, contains each real number lying between 2 and 5 including 2 and 5. To represent a closed interval on a real line, we make solid dots at both endpoints. Figure 1.4b indicates it on the real line. I, E, X, 2, 5, 2 by 5 left open and right closed interval, an interval I with endpoints A and B, a less than B, is called a left open and right closed interval if it contains all real numbers between A and B and also includes only one endpoint B. A left open and right closed interval with endpoints A and B is denoted by A, B, and mathematically is defined as follows: A, B, X, AX, B, equals 1.12. For example, left open and right closed interval 2, 5 contain each real number lying between 2 and 5 including endpoint 5 but does not contain endpoint 2. To represent it on real line, we have to make an open dot at 2 and a solid dot at 5. Figure 1.4c indicates it on the real line. I, E, X, 2, 5, 2 by 5 left closed and right open interval, an interval I with endpoints A and B, a less than B, is called a left closed and right open interval if it contains all real numbers between A and B and also includes only one endpoint A. A left closed and right open interval with endpoints A and B is denoted by A, B, and mathematically is defined as follows: A, B, X, AX, B, equals 1.13. For example, left closed and right open interval 2, 5 contain each real number lying between 2 and 5 including endpoint 2 but does not contain endpoint 5. To represent it on a real line, we have to make a solid dot at 2 and an open dot at 5. Figure 1.4d indicates it on the real line. I, E, X, 2, 5, 2 by 5b, different types of intervals based on the criteria whether its length is finite or infinite. On the basis of the criterion of length of an interval, it may be classified as finite or infinite interval defined as follows: length of an interval, length of each of the intervals A, B, A, B, A, B, A, B is defined as B, A B, minus I, E, length of the interval equals difference of the endpoints. 1.14. For example, if I equals 2, 7, then I, 7 to 5, equals minus equals where I denotes the length of the interval I. Finite interval. An interval is said to be finite if its length is finite. 1.15. For example, if I equals dash 3, 5, then I equals 5 dash 3 equals 5 plus 3 equals 8, which is finite. Interval I equals dash 3, 5 is finite. Infinite interval. An interval is said to be infinite interval if its length is not finite. 1.16. 1.4 Definition, notations and pictorial presentation of a function. Definition of a function. You know about function from school mathematics. You can treat function as a machine if it works in such a way that I, corresponding to each input it gives output, and 2, output is unique for each input. Mathematically, a function is defined as follows: let x and y be two non-empty sets. Then a rule which associates each element of x to a unique element of y is called a function from x to y. X is called domain of the function. Y is called codomain of the function, and the set of only those values of y for which function is defined is called range of the function. That is, the subset y f x for some x equals of y is called range of the function. 1.17 If we treat function as a machine, then the set of all inputs is called domain of the function and the set of all outputs is called range of the function. If we define a function f, z arrow n by y equals f into x equals x square plus 1, x e z, then its visualization as a machine is shown in figure 1.5. Usual notations used for defining a function. A function is generally denoted by f, g, h, etc. In the case of above definition, we write f, x, y and read as f is a function from x to y. 2. A function f, x, y is generally described by writing y f x equals xx, where fx is an expression in terms of x. Pictorial presentation of a function. Visualization of a concept helps in understanding the concept in a better way. Following the same strategy, We are using pictorial presentation of a function, which is an attempt to explain the idea of the function through diagram known as pictorial presentation. The box given in the margin of this page specifies the two requirements for a rule to be a function. These two requirements are also satisfied by the association of daughter with her mother. So, to explain the idea of the function through pictorial presentation, we will continue with example of daughters and mothers. The rule f shown in figure 1.6 a is a function because each daughter has unique mother. i.e., both conditions mentioned in the box are satisfied, and domain of the function f equals set of all daughters equals td, d equals 1 2 3. Codomain of f equals set of all mothers equals m equals 1 2 3 4. Range of f equals set of those mothers who have at least one daughter equals m 1 2 3. Note 2. One point which may come in your mind is that if M4 is a mother, then there should be at least one daughter of the mother M4, but as we know that to become a mother it is not necessary that there should be a daughter. A mother may have only one son or only two sons or more than two sons without a daughter. The rule G shown in figure 1.6 b is not a function because daughter D1 has two mothers M and M12, which is not possible. i.e., condition 2 given in the box is not satisfied. The rule H shown in figure 1.6 c is not a function because daughter D3 has no mother. If the daughter D3 came in this world, then there should be some mother of the daughter D3. i.e., condition I given in the box is not satisfied. The rule phi shown in figure 1.6 d is a function because each daughter has unique mother. We see that both daughters D1 have the same mother. No problem, it is possible. Further, mothers M3 have no daughters. Again, no problem, it is also possible. In this case, the main of the function f d equals 1 2 3 equals set of all daughters. Codomain of the function equals m 1 2 3 4 equals set of all mothers, and range of the function equals 1 to f set of only those mothers who have at least one daughter. Remark 2. If f x y is a function given by y f x equals, then x is known as pre-image of y and y is known as image of x. If y f x equals is a function, then values of y depend on values of x. So, y is known as dependent variable and x is known as independent variable. In descriptive statistics, we also use dependent and independent variables, especially in correlation and regression. In biostatistics, terminology that is generally followed is, independent variable is known as regressor and dependent variable is known as response variable. In the course MST-024 on machine learning, independent variable is known as feature and dependent variable is known as target variable. So, keep this terminology alert in your mind. 1.5 Some special functions having applications in statistics, probability and machine learning. In the previous section you have seen that function is a rule, satisfying two conditions mentioned in the box at page number 18, which associates the elements of one set to the elements of another set. In different courses of the program M.Sc. Applied Statistics, MSCAST, you will use many functions. Some well-known and commonly used functions are discussed in this section. Let us start with the easiest function known as constant function.
Constant function. Suppose you have a special coin having head on both sides. Then whenever you will throw it, each time its outcome will be head. Ignore the possibility of landing on edge like Cholet film. If x is a variable having value 1, if head appears and 0 otherwise, then x will always take value 1. Such type of behavior is represented by a constant function in mathematics and degenerate random variable in probability theory. In mathematics, constant function is defined as follows. Remark 3. If you connect this function with the example of daughters and mothers, then you find that all daughters have 3 as their mothers. But then mother 3 has infinitely many daughters. In real life you will not find a mother who has infinite daughters. So, keep in mind that example of daughters and mothers is given just for better understanding of the two conditions for a rule to become a function. So, limit that example only for understanding the two conditions required for a rule to be a function. The next function that you are going to study is identity function. You will see that identity function associates each element with itself. But in real life a daughter cannot be mother of herself. So, again the same reason example of daughters and mothers is given just for better understanding of the two conditions for a rule to become a function. Keep this point in mind. Identity function. You know from school mathematics that when you multiply a real number with one, outcome will be the same number itself. That is, for any real number a, we have a dot 1 is equal to 1 dot a is equal to a. In the universe of functions, identity function plays the same role as one plays in the family of real numbers. In mathematics, identity function is defined as follows. Let x, a function f, xx, is said to be an identity function if it associates each element with itself, and in general it is defined as polynomials shown in Fig. 1.14, a, b, to Fig. 1.16, a, b, are mentioned in the graphs. From the graphs of these polynomials, note that times even degree and positive leading coefficient, end behavior of the curve on both sides is upward. Refer Fig. 1.16, a. 1.23. Times even degree and negative leading coefficient, end behavior of the curve on both sides is downward. Refer Fig. 1.16, b. Note that in the case of even degree either both ends will be upward or downward. 1.24. Times odd degree and positive leading coefficient, end behavior of the curve will be left downward but right upward. Refer Fig. 1.14, a, and Fig. 1.15, a. 1.25. Times odd degree and negative leading coefficient, end behavior of the curve will be left upward but right downward. Refer Fig. 1.14, b, and Fig. 1.15, b. Note that in the case of odd degree both ends behave opposite to each other, i.e., if one end is upward then another will be downward. 1. 26. Times effect of even multiplicity of a 0, if multiplicity of a 0 is even, then graph of the polynomial touches the x-axis at that point. Refer Fig. 1.15, a, and b, both zeros at x is equal to 2 and 2 are of even multiplicity. So, graphs touch x-axis at both points. In Fig. 1.16, a, and b, two zeros at x is equal to 2 and 3 are of even multiplicity. So, graphs touch x-axis at these points. 1.27. Times effect of odd multiplicity of a 0, if multiplicity of a 0 is odd then graph of the polynomial crosses the x-axis at that point. Further, if multiplicity is 1 then it crosses x-axis at that 0 like a straight line. Refer Fig. 1.14, a, and b, it crosses x-axis at 3 zeros. Also, in Fig. 1.16, a, and b, it crosses x-axis at x is equal to 3.5, but if multiplicity is odd other than 1, like 3, 5, 7, etc., then it crosses x-axis at that 0 such that it tries to flat at 0. Refer Fig. 1.16, a, and b, at the 0 x is equal to 1. 1.28. Exponential function. From school mathematics you know that if you invest rupees p at r% per annum for a period of n years compounded annually, then amount a after n years is given by a is equal to p into 1 plus r upon 100. Suppose p is equal to rupees 1, r is equal to 100% per annum, then formula of amount reduces to is equal to na2 where n is time and 2 represents growth rate. So, if you invest ₹1 for a period of 4 years and growth rate is 2, then after 4 years your amount will be is equal to 4a to 16 rupees. Such type of functions where we have a constant in the base and variable, here time, in the power are known as exponential functions. Mathematically, an exponential function is defined as follows. A function f, r arrow are defined by f into x is equal to a powers x, xer, a greater, a is not equal to 1. S called an exponential function. I.e., the nature of an exponential function is of the form is equal to constant powers variable. Domain and range of the exponential function, in exponential function. Variable x, say, is sitting in exponent of a constant, so function is defined for all real values of the variable x, and hence domain of an exponential function is the set of all real numbers. Suppose f kissed smiley is equal to 2 power x. Then note that values of this function will never be negative and 0 for every real value of x. Logarithm function. In Sec. 1.4 you have seen that function can be treated as a machine, refer Fig. 1.5, which gives unique output corresponding to each input. You know that in an exponential function, if rate is 10 and time is 3, then output, amount, will be 1000. If you are interested in another machine, function, which works in such a way that if output of an exponential function is given as input in this new machine, then its output should be corresponding input of the exponential function. Such a machine, function, is known as logarithm function. In this new machine, rate of exponential function is known as base of the logarithm function. Table 1 explains this inverse relationship between exponential and logarithm functions, and Fig. 1.18 shows both functions as machines simultaneously. Note that when output of an exponential function is given as input to the logarithm function, then output of the logarithm function matches with corresponding input of the exponential function and vice versa. In the last row of the table 1.1, the number e is a special number in mathematics. You have studied expansion of in e power x school mathematics, and the same is given as follows. So, value of e can be obtained just replacing x by 1 in this expansion of e powers x. And the same is given by the infinite series. You will study about infinite series in Sec. 4.4 of Unit 4 of this course. You know that value of e up to 3 decimal place is 2.718. In fact, it is an irrational number. In the course MST-11 you will see that this value of e can be obtained in R by typing exp1 on R console and hitting enter. Domain and range of the logarithm function. Since logarithm function is inverse of exponential function, so range of exponential function will be domain of logarithm function, and domain of exponential function will be range of the logarithm function. Hence, domain of the logarithm function is r is equal to 0, infinity, and range of the logarithm function is r is equal to minus infinity, infinity. 1.34. Graphical behavior of logarithm function. If base is 1, then logarithm function is decreasing, and when its base is 1, then it is an increasing function. Note that 10th October 2010 10 log 10 1, log 102, log 1003, log 10,004 is equal to See. The difference between the input numbers 10, 100 is equal to 10 square, 1000 is equal to 10 cube, 10,000 is equal to 10 powers 4, and output numbers 1, 2, 3, 4. We observe that variation between the numbers 10, 100, 1000 and 10,000 is huge compared to the variation of the output numbers 1, 2, 3 and 4. This is one of the silent features of logarithm function, and due to this it facilitates graphical represents of the numbers with large variations. For example, if you want to compare the sizes of the populations of all Asian countries in the same plot, then you should plot values of population after taking logarithm of population sizes of each country. Without logarithm, plot will not be more informative due presence of two large populations figures of India and China. Fig. 1.19 A and B shows graphical behavior of logarithm function when a is equal to a half, 1, and when a is equal to 2, 1. In the first case logarithm function is decreasing, and in the second case it is increasing. Like an exponential function, there is a special point in the graph of logarithm function. Refer second last row of the table 1.1, which says that log 1 0 2 is equal to. There is nothing special in base 2. You can take any base according to the definition of logarithm function. Its value at 1 will always be 0. Sigmoid logistic function. In the course MST-11 you will study about probability and random variables. One of the silent features of probability is that its value lies between 0 and 1. The value 0 means impossible event and 1 means sure event. Output of sigmoid logistic function also lies between 0 and 1. So whenever there is a requirement to predict value as probability, sigmoid function is one of candidates you can think about. Because of this nature, in the course MST-026 we will use it in neural network as an activation function. Mathematically, sigmoid logistic function gamma r arrow r is defined by gamma into x 1 upon 1 is equal to e powers x x e r. 1.42. Absolute value function or modulus function. If a machine behaves in such a way that its output is exactly the same number as was the input, in the case its input is 0 or positive number, and its output is negative times the input, in the case input is a negative number, then behavior of such a machine matches with absolute value function or modulus function. Mathematically, modulus function is defined as follows. Unit step function. If a machine behaves in such a way that its output is 1, in the case its input is 0 or positive number, and its output is 0, in the case input is a negative number, then behavior of such a machine matches with unit step function. Mathematically, unit step function is defined as follows. Greatest integer function. If for a given real number x, we have a machine which gives output as the greatest integer less than or equal to x, then such a machine is known as greatest integer function in mathematics. Greatest integer function is denoted by x. Thus, the piecewise function f r arrow r. Graphical behavior of greatest integer function, we have seen that it is a piecewise function having infinite number of pieces. Its graphical behavior is shown in Fig. 1.23 b. Consider the interval 1, 2. Note that here we have made solid dot at the point 1, 1, because at x is equal to 1 function takes value 1. But at the point 2, 1, we have made an open dot because at x is equal to 2 function takes value 2 not 1, hence solid dot at the point 2, 2, and open dot at the point 2, 1. Similarly, graph is plotted in other intervals. Even function, if a function is such that it takes the same value at x and x, then it is known as even function. So, even function is defined as follows. A function f kissed smiley is said to be even function if it satisfies f kissed smiley for all points x of the domain of the function f is equal to 1.56. 1.6 Summary. A brief summary of what we have covered in this unit is given as follows. Times in mathematics and statistics, quantity means those things on which for basic mathematical operations addition, subtraction, multiplication and division can be applied. Times a quantity which remains same, unchanged, throughout a particular problem or distribution is known as a constant quantity. Those types of constants which always remain the same, unchanged, independent of the place and time are known as fixed constant. Those types of constants which remain same in one problem but may vary from problem to problem or distribution to distribution are known as arbitrary constants or parameters. Times a quantity which may change its value even in a particular problem is known as variable. If the nature of the quantity is such that its possible values can be written in a sequence, then such a quantity is known as discrete in nature or discrete variable. If the nature of the quantity is such that it can take any possible value between two certain limits, then such a quantity is known as continuous in nature or continuous variable. Let B the set of all real numbers. Then a set R is said to be an interval if whenever A, B and A, B then XEI times an interval is said to be finite if its length is finite. An interval is said to be infinite if its length is not finite. Times let X and Y be two non-empty sets. Then a rule which associates each element of X to a unique element of Y is called a function from X to Y. X is called domain of the function. Y is called codomain of the function. And the set of only those values of Y for which function is defined is called range of the function. Times if YF kissed smiley is equal to is a function, then values of Y depend on values of X. So, Y is known as dependent variable and X is known as independent variable. Times in different courses of the program MSc Applied Statistics, MSCAST, you will use many functions. Some well-known and commonly used functions are discussed in this unit, such as constant, identity, polynomial, exponential, logarithm, sigmoid, modulus, sinum, greatest integer, even and odd functions. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.